Okay, so I want you to just picture your morning commute for a second.
Right.
You back out of your driveway, you hit that specific pothole you always swear you're going to miss, you merge onto the highway, maybe you cross a bridge. It all just feels so solid.
Like geology, but, gray.
Exactly. But the reality is, every single inch of that experience, the slope of your driveway, the curvature of that off-ramp,
Even the way the water drains off the road during a storm.
yes, it all started as a ghost.
A ghost. That's a new one for me.
Well, a digital ghost. It started as a line on a screen. Or, if we go way, way back, a graphite smudge on a piece of vellum paper.
That's very true. Before it was concrete, it was all just geometry.
Welcome back to the deep dive. Today we are peeling back the asphalt. We're looking at the hidden language that dictates, well, how our physical world is put together.
We are decoding the built environment.
And to do that, we're looking at a source that sounds, I'll admit, dry as a bone, but is actually hiding some incredible secrets. Autodesk Civil 3D 2025 Fundamentals.
Specifically Chapter 1, and I know what you're thinking. It sounds like we're about to read you a software manual.
Right.
But this isn't about which button to click. This text is actually a really deep primer on civil drafting technology. It's the who, what, where, and why of mapping the Earth.
It really is. It's about taking the messy, chaotic, organic reality of our planet, mud, trees, hills, and translating it into precise, clean data that we can actually build on. And by the end of this, I want you to have that Neo in the Matrix moment where you look at a construction site and you don't just see dirt, you see the code.
The as-built, the contours, the elevation data, yeah, it totally changes how you see the world.
So let's get into it. The source starts with a bit of a history lesson that I honestly didn't see coming. It claims civil engineering is the second oldest form of engineering.
Superseded only by military engineering, which, if you really think about human history, that tracks perfectly.
It does. I was thinking about it. The first engineering problem isn't how do I get fresh water to my village? It's how do I build a wall so the other guys don't take my village?
Exactly. Fortifications came first. But then, okay, once you're secure, you need roads to move your troops. Then you need roads to move your goods.
And that's the shift.
That's the shift. From the military application to the civilian application, that is literally where the term civil engineering comes from. It separates the bridge builder from the bomb maker.
And today, that umbrella is just massive. I mean, the source lists everything from bridges and canals to dams, harbors. Basically, if it's huge, heavy, and doesn't move.
A civil engineer probably signed off on it. Planning, design, construction, maintenance. It's the whole infrastructure of civilization.
But here's the distinction I want to nail down early on, because our source is specifically about civil drafting. I feel like people confuse the engineer and the drafter.
Oh, all the time.
Is it like an architect and a builder?
It's, a better analogy might be the relationship between, say, an author and a translator.
Ooh. Okay, I like that. Unpack that for me.
So the civil engineer, the PE, the professional engineer, that's the person with all the legal weight on their shoulders.
Right.
They've got the 4-year degree. They've passed that absolute nightmare of an exam. They are the ones who calculate the load limits and say, yes, this bridge will hold 50 tons. If it falls down, they're the one going to court.
So they provide the scientific truth, the calculation.
Correct. But the drafter is the one who takes that calculation and turns it into a visual instruction manual that a construction crew can actually read and build from. The engineer might say, we need a 2% slope here, but the drafter creates the model that shows exactly where the earth needs to be moved to make that happen. They're the bridge between the math and the mud.
And the tools for that have gone through a complete revolution. The source mentions geomatics. It sounds like something out of science fiction.
It's basically surveying on steroids. Surveying kind of implies a guy with a stick and a chain measuring a field. Geomatics is the collection, storage, and management of geographic data using satellites, lasers, databases.
That database part seems to be the key difference.
It is.
In the old days, a map was just a drawing. If you erased a line, poof, the data was gone. Today, with things like GIS and CAD, the line on the screen is just a visual for a database entry.
Exactly right. Think about the efficiency jump. In, say, 1950, if you wanted to map a highway route through a forest, you had to send a team out there for weeks with machetes.
Right.
They'd come back with notebooks full of numbers, and someone would spend days, maybe weeks, hand-drawing the map. And if they made a mistake...
You go back to the woods.
You go back to the woods today. You can fly a drone over it with LiDAR that's laser scanning. It digitally strips away the trees, measures the ground to within a centimeter, and feeds that directly into the software.
Wow.
What took weeks now takes a few hours. It's not just drawing anymore, it's spatial data management.
Okay, let's talk about the output of all this data. The map. The source gets into the anatomy of map borders, title blocks, legends, north arrows. And I'll be honest, at first I was like, okay, I know what a legend is.
Sure.
But then I read deeper and I realized this isn't about making it look nice. It's about liability.
100%. In civil drafting, ambiguity is the enemy. It is expensive and it is dangerous.
So like the title block, for instance. It just seems like a box with the company name in it. Bureaucracy.
Right, but imagine you're a contractor fixing a sewer line. You pull a drawing from a big pile. It looks right. You start digging. And then boom, you've hit a gas main.
Oh, no.
Why? Because you were looking at the preliminary draft from 3 months ago, not the final construction document. The title block is the only thing that tells you which is which. It's a legal tag.
So if it's not filled out correctly, the drawing is worse than useless. It's a trap.
Precisely. And the same thing goes for the north arrow. Seems trivial, right? But if you orient a building incorrectly on a site, because that arrow was wrong, you might have the loading dock facing the main street instead of the alley.
That's $1 million mistake.
Easily.
And scale. This is where I think we all get tripped up. We think of scale as just zooming in. But in drafting, it's a mathematical promise, isn't it?
It's a ratio. 1 inch equals 100 feet. That lets a contractor take a physical ruler, put it on the paper, and know exactly how much pipe to order. If the drafter prints that map at the wrong size or just messes up the ratio,
The contractor orders the wrong amount of material.
and you get expensive errors from these so-called basic elements.
Okay, let's move to the different types of maps. This is where I started having those aha moments. The source lists a bunch, but the topographic map, the topo, that's really the foundation, isn't it?
It is. You can't really build anything without a topo map.
And the magic trick of the topo is the contour line. I've seen these on hiking maps, the squiggly lines. But what are they actually showing us?
The best analogy I've ever heard is the bathtub ring.
The bathtub ring, okay.
Yeah, so imagine a hill is sitting in a giant bathtub. You fill the water up to, say, 100 feet deep. The water leaves a ring around the hill. That's a contour line. Every single point on that line is at exactly 100 feet of elevation.
Oh, I get it. So then you raise the water to 110 feet and make another ring.
You got it. Exactly. So when you look down at the map, if those rings are super close together,
It means the water rose 10 feet but didn't have to spread out very far horizontally. So it's steep.
correct, it's a cliff.
Right.
And if the lines are really far apart, the water had to spread way out to get 10 feet higher. That's a gentle slope.
That's brilliant. You're seeing 3D terrain on a 2D piece of paper.
That's the whole point.
Then you have the USGS quadrangle maps.
Yeah.
And I learned something new here about the colors. I just thought, map makers liked green for forests and blue for water.
It feels intuitive, but it's actually a strict standard.
It has to be, right?
Yeah, it has to be. You need instant recognition. If you're a firefighter looking at a USGS map during a wildfire, you don't have time to check a legend. You just need to know that blue is water, green is vegetation, brown is contours, and black is anything man-made.
It's a visual shorthand that saves lives.
It can, yeah.
Then we have what are called thematic maps. These tell a specific story. The book used an example from Alaska showing permafrost. And this goes back to what you said about liability.
Right.
That map isn't just here is the dirt, it's here is the danger.
Exactly. Permafrost is frozen ground. If you build a road on it and it melts, the road just collapses. So a thematic map strips away all the noise. It might not show every house or street sign, but it highlights that one critical variable.
It forces you to focus on a specific problem.
Yes.
Speaking of specific problems, let's talk about military maps. I just assumed a map is a map. But the military does things very differently.
Very differently, and for very good reasons. The stakes are, life and death.
The thing that just blew my mind was how they measure angles. We use degrees, 360 in a circle. Simple. The military uses mils.
Mils, it's short for milliradians.
And the math is so weird. A circle has 6,400 mils. Why on earth do they need that?
Well, think about what they're doing. They aren't just navigating, they're firing artillery. If you are shooting a cannon at a target 20 kilometers away and your calculation is off by 1 single degree,
You miss by a lot.
you miss by hundreds of meters. You might hit a village instead of a bunker. A degree is just too big a slice of the pie. A mil creates 6,400 slices. It allows for unbelievable precision.
So it's just a much, much finer ruler.
Exactly. And then you have the lighting problem.
Oh, right. The red light thing. This is fascinating.
It's pure functional design. In a tactical situation at night, you can't just turn on a bright white flashlight to read your map.
You'd give away your position.
Yeah.
And you'd ruin your night vision.
Those soldiers use red lights. But if you look at a standard map under a red light, red ink disappears. It reflects red light, so it looks white.
Yeah.
So if your enemy positions are drawn in red, they become invisible.
Which, not ideal.
Put it mildly. So military maps use specific color palettes designed to stay high contrast even under red light. It's a detail a civilian drafter never thinks about, but it's critical for that user.
That is just so cool. It's a reminder that the user always determines the design.
Always.
Okay, let's jump from paper maps to the digital realm. The source throws a ton of acronyms at us here. DEM, DSM, DTM. It felt a bit like alphabet soup, so let me see if I've got this straight.
Go for it.
Okay, a DEM, digital elevation model. This is the naked version of the Earth. Like if I shaved it bald, no trees, no houses, just dirt.
That's a perfect way to put it. It's the bare earth model.
Then you have the DSM digital surface model. This is the real one. It includes the trees, the buildings, everything. It's what a bird would actually see.
Correct. We call it the first return data.
So here's my question. Why would you ever need the bald one? If I'm building a road, don't I need to know where the trees are?
You do, but mostly so you can plan to cut them down. But think about water again. So much of civil engineering is a battle with water.
Right.
To understand how water flows over the land, you need to know the shape of the land, not the shape of the tree growing on it. If you use a DSM to model drainage, the computer thinks the tree canopy is a solid hill and you get the wrong calculations. You need the DEM to understand gravity.
That makes perfect sense.
Yeah.
Okay, and the third one, DTM, digital terrain model.
This one's a little more nuanced. A DEM is usually a grid of pixels, like a photo. A DTM is often a vector model, so lines and points. It's used to define the break lines.
Break lines.
The sharp changes in slope, the ridge of a cliff, the bottom of a ditch, the curb of a road. A DTM connects those specific features, giving engineers a super accurate framework for analyzing slopes. It's less like a photo and more like a wireframe mesh.
So we have our data. Now we need to visualize the project. We start with the plan view, the bird's eye view.
Going straight down, yep.
But there's a difference between a vicinity map and a site plan. Is that just about the zoom level?
It is, but the purpose is different. A vicinity map is zoomed way out. Its only job is to show the delivery guy how to find the site. It's off exit 5, turn left at the gas station.
And the site plan
is zoomed way in. This is the legal definition of the project. It shows exactly where the property lines are, where the building sits to the inch, where the driveway connects to the road. It's what the surveyor uses.
But just looking down isn't enough. We need to see inside things. And this is where sections come in. The cake analogy is the only way I can get this.
It's a classic for a reason.
So the plan view is looking at the top of a frosted cake. You can't see the filling. A cross-section is slicing that cake in half and pulling it apart.
You got it. In engineering, we use a cutting plane line on the map to show where we made the slice. Then we draw the inside. You can see the layers of the road, asphalt, then gravel, then compacted soil. You see pipes buried 6 feet down. You can't build it without seeing those layers.
And a profile is just a special kind of section. Right.
It's a section that follows a path. Instead of slicing across the road, you slice along the center line of the road for miles. It shows you the roller coaster ride, the ups and downs.
But I noticed something really weird in the example drawings. The profiles. They looked just wrong.
Yeah.
Like the hills looked incredibly steep, like mountains. But the description said it was a gentle road.
Yes, that's called vertical exaggeration.
Is that safe? I mean, isn't distorting the drawing dangerous?
It seems counterintuitive, I know, but it's actually safer. The problem is the Earth is big, but relative to its width, it's actually pretty flat.
Okay.
If you drew a mile-long road at true scale on a piece of paper, the vertical changes, the little dips and bumps, would be microscopic.
Yeah.
You wouldn't be able to see a low spot where water might collect and cause a problem.
So you stretch it vertically?
Usually by 10 times. So 1 inch horizontal might be 100 feet, but 1 inch vertical is only 10 feet. It makes a gentle hill look like Everest, but it lets an engineer spot a drainage problem instantly. It highlights potential errors.
So it's a deliberate distortion to reveal the truth.
That's a great way to put it, yes.
Speaking of truth, we need to talk about the as-built. This was my absolute favorite concept in the whole chapter.
It's maybe the most important document in the life cycle of any project.
So walk us through it. We have the design drawings, the plan, That's the perfect world, right?
That's the theory. In the plan, every corner is a perfect 90 degrees, the ground is exactly where the survey said it was, and the pipe fits perfectly. It's the platonic ideal of the project.
And then construction happens.
Reality ensues. The excavator hits a boulder the size of a car that wasn't on the survey. They have to move a pipe 3 feet to the left. The steel beams show up an inch too short.
Improvisation.
It's just necessity. You can't stop a multi-million-dollar project for every little surprise. You adapt, but, and this is the critical part, you have to write it down.
And that's the as-built.
Exactly. After construction is done, a surveyor goes back out and measures what is actually there. The drafter takes the original plans and updates them to show reality. The pipe is actually here, not there.
Why is that so important?
Because 10 years from now, when a maintenance crew needs to find a shutoff valve to stop a massive leak, they don't want the drawing of where the valve was supposed to be.
Oh, wow.
They need to know where the contractor actually put it. If they dig in the wrong spot because they used the original design, not the as-built, the whole building floods.
It's the difference between theory and practice.
It's the document that bridges the two.
This leads us to the final piece of the puzzle. The rules. The source. So many acronyms. ANSI, ISO, ASME. Why do we need so many rule books just to draw lines?
Because we're all trying to build one global machine. If I'm a drafter in New York and I draw a dashed line on a plan to mean tear this wall down, and I send that plan to a contractor in California.
He needs to know that line means tear it down, not build a new fence here.
Exactly. Standards are a common language. If every firm invented their own symbols, it would be chaos. Buildings would be collapsing because nobody would know what the drawings meant. Standards like ANSI and the NCS ensure we're all speaking the same dialect.
But the source makes this distinction between a standard and a code, and I have to admit, I always thought those were the same thing.
That's a common misconception, but there's a huge legal difference.
Okay, so what is it?
A standard is basically a suggestion, a best practice. The ASME might say it's best practice to draw your arrows this way. If you don't do it, you're just, being difficult.
Right.
But the building code or the fire code, those are standards that have been adopted by the government and given the force of law. If the fire code says exit paths must be 44 inches wide and you draw them at 40 inches,
And we're breaking the law.
you are. The city won't give you a permit. And if you build it anyway and there's a fire, you could go to jail. Codes are standards with teeth.
Which brings this all back to ethics. The source talks about intellectual property, sure, but it also gets into personal ethics. Be dependable. Obey the laws. It sounds a little simple, but the stakes are so high here.
Much higher. In this field, be dependable isn't about showing up on time. It's about checking your math. If a drafter gets lazy and copies and pastes a detail from an old project without checking if it applies, people can die.
That's the real weight of the profession.
It is. Organizations like the ADDA have certification programs just to verify that drafters understand these responsibilities. You aren't just making pretty pictures, you are writing the instructions for public safety.
So, we've gone from Roman forts to LiDAR drones. We've looked at the difference between the bare earth DEM and the real-world DSM.
And the crucial importance of a red light on a battlefield.
Right. What's the big takeaway? How should we look at our city differently tomorrow?
I think for me, it's realizing that the built world is just hyper-intentional. We walk around and think cities just sort of happen. But every curb height, every slope of a sidewalk, every location of a telephone pole, it was all debated, calculated, and drawn by a human being trying to solve a puzzle.
It's a matrix of decision.
It is. And it's a constant negotiation between the perfect plan and messy, messy reality.
I want to leave everyone with that thought about the as-built again. In a world where we all obsess over perfection, the perfect photo, the perfect plan, the civil drafter is the one person professionally obligated to document the imperfections.
The as-built is the truth.
The as-built is the truth.
Right.
I love that. Thanks for helping us decode the world today.
Well, always a pleasure.
And to our listeners, next time you see a surveyor on the side of the road with that tripod, give them a nod. They're just updating the database. Thanks for listening to The Deep Dive. We'll see you next time.